So, we will continue with the normal shock relation. So, I will write down the equations which we had derived the other day. The first equation in a normal shock is of course T01 T0x equals T0y from H0x equals H0y. From continuity we have derived Px by Py equals 1 plus gamma my square divided by 1 plus gamma mx square, okay, where x and y are states before the shock and after the shock. We have also seen Tx by Ty to be 1 plus gamma minus 1 by 2 my square divided by 1 plus gamma minus 1 by 2 mx square. Our P2 from continuity equations Px mx root Tx equals Py my root of Ty. We have also derived the equation for Mach number after the shock in terms of Mach number before the shock. So, your my square is mx square plus 2 by gamma minus 1 whole divided by 2 gamma by gamma minus 1 mx square whole minus 1. Now, we will derive some equations further to this. So, I have this equation which we have also seen to be of this form. This is 1, this is my, this is mx, 1. Now, what we will do is, so now we know our my in terms of mx. So, if I know my Mach number before the shock, I know my Mach number after the shock. So, likewise, if we can we relate these ratios in terms of mx, okay, or Tx by Ty or rho x by rho y. If that is possible, then we can have something called shock tables, where I would write my mx, then I can get my my, then I can get these ratios which we have been talking about. Okay. So, what do? I substitute my in these equations. Say for example, I substitute my in Px minus Px by Py equation. So, I would eliminate my my with this. Okay. So, I take equation, so let us equation 1, this is equation 2, equation 3 and equation 4. Okay. So, I take equation 2 which I will rewrite here as Px by Py equals 1 plus gamma my square divided by 1 plus gamma mx square. I substitute for my in terms of mx. So, I am not going to derive the simplified form of this equation, but I will tell you the procedure to get this. This is nothing but mere algebra divided by 1 plus gamma into mx square divided by 1 plus gamma mx square. Okay. So, I have replaced my in terms of mx, that is all I have done. So, the final equation would look something like one plus gamma 2 gamma by gamma minus 1 into mx square minus 1. Okay. So, I have the pressure ratios before and after the shock in terms of my Mach number before the shock. Likewise, I can get T. So, this is Ty Py by Px. Okay. So, there is a correction here. This is Py by Px is this, and Ty by Tx, which is also my Hy by Hx equals some very lengthy equation into 2 plus gamma minus 1 m1 square divided by gamma plus 1 into mx square. Okay. So, I have my pressure ratio before and after, the static pressure ratios before and after the shock, static temperature, temperature ratios in terms of Mach number. Okay. I can also get my density from that is a very simple relation, which I can get it as this. We can write this as V1. We can write this as V1 square by V1. I will write it as y and x is the notation that we were using. So, I will continue with that. So, this would be Vx square Vy into Vx, which Vx dot Vy we have derived to be okay. There is a bracket here. Okay. There is mx square minus 1. There is a bracket there. Yeah. Thanks. Okay. So, the denominator Vx dot Vy, we know it as A star square, which is now nothing but mx star square. Now, mx star we know already in terms of mx, which is nothing but gamma plus 1 divided by gamma plus 1 mx square divided by 2 plus gamma minus 1 mx square, correct? Yes. So, this is rho y by rho x, which is also equal to Vx by Vy. So, your star m star before the shock is your ratio of your densities. So, now I have written these, if you look at the tables which I was talking about, I have written all these ratios Tx by Ty, Vx by Vy, rho x by rho y, all in terms of my Mach number before the shock. So, if I know the Mach number before the shock, I get all these values. Okay, so I can tabulate that, and that is what you have it in shock table. This depends only on your gamma and probably R. Okay, so depending on your gamma value, you get all these results. So look at your gamma in the tables. Look for the shock tables. This is the shock tables that similar to your isentropic tables what you have. So in the book, after the isentropic table, you will see something called a shock table. So look for the appropriate gamma, find your Mach number before the shock, and you get all these quantities after the shock. Now it will be interesting to see how this varies when mx approximates to 0, approximates to infinity. So that is in the limit mx approximating to infinity, what is your py by px? Okay. So I would get py by px in the limit approximating m to infinity is infinity, then limit mx tending to infinity, my ty by tx also approximates to infinity. If you look at this equation, I can get infinity there. But what about density? Rho y by rho x approximates to, if I differentiate that, I would get gamma plus 1 by gamma minus 1. Okay. And what about m2 or my? So mx and my are the notation that's given in the shock tables. Typically, many books will deal with as 1 and 2, which is the same thing. So, so if you look at your equation here, as m tends to infinity, what is your Mach number at after the shock? Okay, so you can do this, and you would find this to be gamma minus 1 by gamma plus 1. So you can try these things as your homework. Get this equation, find the limits as mx tends to infinity, what are these values? Okay. So these two asymptotically reaches to these values. Okay. So if I plot these values, I would I will rub this. Number, and let us say P, this is what I have written here is Py by Px. So Mach number starts from 1, so this is mx. So depending on my mx, I will have different values of my property ratios, and mx equals 1, my pressure ratio is going to be okay. So this would be root of gamma minus 1 by 2 gamma. So as my m infinity tends to infinity, my is root gamma minus 1 by 2 gamma. Yeah. So, it would be this. Okay. Yeah. So, this is the correction there. Root gamma minus 1 by 2 gamma is your asymptotic value of your my. So, let us draw that first, my. So, it starts from 1 and then goes like this. The asymptotic value is root gamma minus 1 by 2 gamma. So, that would be my asymptotic value. So, it should not cross. So, as mx tends to infinity, this value will approach to this value. Okay. Now, when mx equals 1, so this is my my. Now, I will draw py by px. As mx tends to infinity, this ratio would approach infinity. So, at mx equals 1, this ratio is 1, as we had already seen, or if you can substitute that as in the relation which you have just now seen, you will see this as 1. Mx, I have the ratio value 1 here, and this py by px. This approaches infinity as mx tends to infinity. T by tx also approaches infinity when this approaches infinity, but at a slower slope. Now, you can have this will not cross. So, your temperature ratio would go like this, your pressure ratio would go something like this. And your density approaches some asymptotic value. So, let's it again starts from 1 when mx equals 1. So, this would go to some constant value which is this, which is gamma plus 1 by gamma minus 1. So, I have my rho y by rho x approaching an asymptotic value when mx tends to infinity. Okay. So, I would the density line is shown in the red color. It approaches the asymptotic value which we had just now written. Okay. So, as m tends to infinity, my density would approach to this particular asymptotic value. Both temperature and pressure ratios approaches infinity as mx tends to infinity. Okay. Now, we look at what is the value of P0x by P0y. Which we have written in terms of Mach number the other day, which is which we obtained it as this okay, this P0 in terms of y by Py, this is Py, Px, Px, Py, Px, 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 Px. So, this quantity now we know in terms of mx, this is anyway in mx, this quantity we know in my, which we can write it in terms of mx. Okay. So, all this we can now write it in terms of mx. Okay, which is, I will write it down. This again you can derive it yourself. 1 by gamma by 2 mx square divided by 1 plus gamma minus 1 by 2 mx square whole to the power gamma by gamma minus 1 into 1 by 2 gamma by gamma plus 1 mx square minus gamma minus 1 by gamma plus 1 to the power 1 by gamma minus 1. So, I have my P0y by P0x in terms of mx. So, for a given mx I have this ratio, which again we know that P0y is going to decrease. So, I would from the entropy condition we know that P02, P0y should always be less than P0x, and the ratio would decrease like this. So, I would write P0y by P0x. If it is when it is 1, you have the trivial solution, and it goes something like this. And all these quantities you can get it from the gas tables, where you give you have a separate section on shock relations. So, the moment you have the flow before the Mach number before the shock, I can get all the quantities after the shock, all these ratios. So, if I look at the TS diagram, so what am I drawing? I have a flow and then suddenly I see a shock. So, this is x, this is y. So, up to this is isentropic flow. After the shock also is isentropic flow. Shock is a non-isentropic flow. Okay. Now, we are going to draw this particular process. So, this the flow goes from 1 to x, and then x to y, and then from x to y to 2. So, I have a flow that is going from state 1 to state x. Now, this is a expansion process. So, my flow is accelerating or whatever. I have a Mach number at x which is greater than 1. Okay, that is the only condition I need at present. Now, the moment it encounters a shock, there is an entropy change. So, there is a dx. So, if I take Ty by Tx, that is increasing. After the shock, it is increasing. So, my Ty is greater than Tx. So, I have a process that takes me to some location here which is my y. Okay. Now, from there I still go an isentropic process to 2. The stagnation point of x is somewhere here, stagnation point of y is somewhere here, both are same. T0x equals T0y equals T01 equals T02. So, the stagnation point of all these, stagnation temperature of all these points are same. Okay. So, the process from 1 to 2 with a shock in between is this, 1 to x, then x to y, and then take another isentropic process to 2 with T01 same. So, T0x equals T0y equals T01 equals T02, but the Tx, because of the shock, Ty has gone up and then comes down. Now, draw the same thing in a PV diagram. So, I will draw this side close by. So, I have a pressure. So, this is pressure P1. So, P1 isentropically goes to Px. Okay. Then there is a non-isentropic process in which Px by Py, Py by Px increases. So, Py by Px increases or Py is greater than my Px. So, there is a sudden jump in pressure the moment you encounter a shock. So, I have an isentropic process here and then there is a jump in pressure. So, there would be some jump in my pressure. So, this goes to next line. So, this is my x, this is my y. Okay, it may not be like this. So, this is my nu, this is my v. So, my density would also increase. So, it has to go somewhere here such that my, no, it is somewhere here. So, the density has increased or the volume has decreased. So, this would be left of my point here. So, this would be Py. So, there is a decrease. So, my rho x is smaller than my rho y. Okay. So, this is my Py. Then again an isentropic process which will take you to location 2. Okay. So, when you draw the Ts diagram, the y is your at your right of your x condition x state, right of your original state before the shock. In the PV diagram, because the density is increasing, it will be left of your original state or before the shock. Okay. So, it goes from 1 to x isentropically, then a non-isentropic process happens where you increase your density. So, it goes to left and then from there to state 2. Okay. So, I will remove this unwanted curve. Okay. So, there is a ds that is happening, which is this ds. This ds or delta s is given by the relation P0y by P0x equals e power minus delta s by r. So, your delta s is given from this relation where you could find your delta s and appropriately point to your x location.